In the beginning, long before our sun ignited, the universe was filled with clouds of hydrogen and helium, the most basic elements born from the cooling fireball of the Big Bang. These clouds drifted, collided, and gathered under the pull of gravity. In their slow collapse, they grew hotter and denser, until pressure in their hearts became so intense that hydrogen atoms fused into helium. A star was born. Stars live as engines of fusion. In their cores, atoms are forced together despite the natural repulsion of their electric charges. Hydrogen fuses to helium, helium to carbon and oxygen, then into heavier elements in sequence. Every step releases energy that pushes outward and prevents gravity from crushing the star in on itself. This balance between the pull of gravity and the push of fusion defines the life of a star. Small stars, those with less than 8 times the mass of our sun, live long and quiet lives. They burn their fuel slowly, sometimes for tens of billions of years, before fading into white dwarfs. A white dwarf is a cinder, a leftover core made of carbon and oxygen, no larger than Earth but holding nearly the mass of a sun. These stellar remnants shine faintly, cooling over trillions of years, awaiting the deep future when the universe itself grows cold. But larger stars, those 8 or more times the mass of the sun, follow a more violent destiny. Their immense gravity squeezes their cores harder, burning fuel faster, forging heavier elements with each stage of collapse. They create neon, magnesium, silicon, and finally iron. Iron is the end of the line, for fusing iron consumes more energy than it gives. When iron fills the core, fusion halts, and the delicate balance between pressure and gravity is broken. In a moment lasting less than a heartbeat, the star's core caves in. Outer layers crash inward at speeds of thousands of kilometers per second, then rebound violently, tearing the star apart in a cataclysm known as a supernova. The brilliance of such an explosion can outshine entire galaxies, and in that fury, new elements are hurled into space, seeding future planets, life, and civilizations. What remains after such a death depends on the star's mass. If the collapsing core weighs less than about 1.5 times the mass of our sun, it becomes a white dwarf. If it is greater, but not more than about 3 times the sun's mass, the core squeezes down into a neutron star. These objects are made almost entirely of neutrons, packed so tightly that a spoonful would outweigh a mountain. A neutron star is only about 20 kilometers across, yet it can contain more mass than 2 suns. When the collapsing core exceeds that threshold of 3 solar masses, gravity wins completely. Nothing can halt the fall, not even the degeneracy pressure of neutrons. The result is a black hole, a region where space and time themselves collapse, and nothing, not even light, can escape. Black holes are the ultimate expression of gravitational collapse. But where do quark stars fit in this hierarchy? They are not white dwarfs, and they are not neutron stars, though they share kinship with both. And they are not black holes, for they may stop just shy of that final abyss. A quark star, if it exists, would be born when matter is crushed past the limits of neutrons, breaking them apart into their constituent quarks. Instead of neutrons locked together, the star would be a sea of up, down, and possibly strange quarks. Neutron stars are already extreme, nearly unimaginable in density and power. But what if nature has an even stranger trick? A state of matter beyond the neutron star, a deeper collapse that does not yet fall into the black hole's eternal shadow. Could quark stars be the missing link, a hidden chapter in the story of stellar death? The lives and deaths of stars lead us here, step by step, from gentle white dwarfs to neutron stars to black holes. At each stage, matter is pressed harder, pushed deeper, revealing new laws of physics. Neutron stars are already a miracle of pressure, balanced against collapse. But what if there is something beyond, something stranger than neutrons themselves? The birth and death of stars is not only the foundation of astrophysics, but the engine of the cosmos itself. To understand how stars live is to see the heartbeat of the universe, a rhythm that shapes galaxies and creates the ingredients for life. In their simplest form, stars are massive spheres of plasma held together by gravity, yet their inner workings are far from simple. Every photon of light, every shimmer in the night sky is the echo of nuclear fire burning in distant hearts. The life of a star depends on its mass, and that one variable decides its entire fate. Stars like our Sun spend billions of years fusing hydrogen into helium through a process called the proton-proton chain. Each fusion reaction releases energy as light and heat, and this radiation pushes outward, countering the inward force of gravity. For a sun like ours, the balance is delicate but stable, and it has lasted for nearly 5 billion years. It will continue for about 5 billion more before change becomes inevitable. When hydrogen runs low in the core, fusion slows and the balance tips. Gravity squeezes the star inward until helium ignites. The star swells, turning into a red giant. In our Sun's case, this will mean the swallowing of Mercury and Venus, and perhaps even Earth, before the outer layers are shed into space in a beautiful planetary nebula. The core that remains will shrink into a white dwarf, glowing faintly for countless eons as it cools. But when we turn our gaze to massive stars, those more than 8 times the mass of our Sun, we see a far more turbulent story. These giants blaze with ferocity, burning hydrogen in only millions of years, a mere blink compared to the calm of smaller stars. They step rapidly through heavier elements, their cores burning hotter and faster, each layer like the skin of an onion. At the heart lies the eventual enemy, iron. Once iron builds up, fusion stalls. Unlike lighter elements, fusing iron consumes energy instead of releasing it. The core can no longer resist gravity's crushing pull. The collapse is instantaneous. In less than a single second, the iron core collapses from thousands of kilometers across to a sphere only tens of kilometers in size. The outer layers crash inward, then rebound in an explosion so violent it tears the star apart. This is a core collapse supernova, among the most powerful events known in the universe. The light from such an explosion can outshine entire galaxies. Neutrinos, ghost-like particles that almost never interact with matter, pour out in unimaginable numbers, carrying away most of the energy. What remains depends entirely on how much mass is trapped in the core. If the collapsed core is below the critical limit, it stabilizes as a neutron star. But this stability is precarious, balanced on the physics of degeneracy pressure, a quantum law that forbids neutrons from occupying the same state. If the remnant core exceeds roughly 3 times the mass of the Sun, not even neutron degeneracy pressure can resist the fall. Then nothing can halt gravity, and the result is a black hole, an invisible sphere whose boundary is called the event horizon. The existence of black holes has been confirmed through many lines of evidence, from the orbits of stars around invisible companions to the detection of gravitational waves rippling through space when 2 of them collide. They represent the final triumph of gravity. Yet there may be another step in the chain, hidden in the space between neutron stars and black holes. This is where the idea of quark stars emerges, as an intermediate state of matter that breaks the limits of the known. The concept of a quark star arises from the fact that neutrons themselves are not fundamental. They are made of smaller particles called quarks, bound tightly together by the strong nuclear force. Under pressures greater than anything inside an atomic nucleus, neutrons may no longer remain whole. Instead, they could dissolve into a sea of quarks, stripped of their structure but still bound in a collective state. If this occurs before gravity pushes the star all the way into a black hole, the result might be a quark star, smaller and denser than a neutron star, but not yet collapsed beyond return. The deaths of stars, then, may not simply end with 3 categories of remnants. Instead, there may be a hidden fourth, a rare and exotic form of matter that bridges the gap between the known and the unknown. Quark stars, if they exist, would be among the strangest objects in the universe, stranger even than the neutron stars they would replace. From gentle dwarfs that cool into cinders, to supernovae that tear galaxies with their brilliance, to neutron stars that squeeze matter into unimaginable densities, the hierarchy of stellar death is already full of extremes. Yet, the possibility of quark stars whispers of something beyond. It hints that the universe may have another secret, one revealed only under the most crushing pressures and the most violent deaths of stars. The deaths of stars shape the very fabric of the universe, but they also push the boundaries of our understanding of matter itself. When we study the remains of supernova explosions, we do not just witness destruction, we witness creation of new worlds and new laws of physics. White dwarfs, neutron stars, and black holes are more than remnants. They are laboratories of the extreme, where matter is tested under pressures that can never be reproduced on Earth. Consider the white dwarf. It is the simplest of stellar corpses, yet even here the laws of quantum mechanics decide its fate. A white dwarf survives not because of nuclear fusion, but because electrons resist being squeezed together. This resistance is called electron degeneracy pressure, and it is a quantum rule that says no 2 electrons can occupy the same state. As the star cools, its light fades, but this pressure holds the remnant against further collapse. It is quiet, stable, and long-lived, a glowing ember of a once radiant star. Neutron stars are far more violent creations. When the core of a massive star collapses, gravity overcomes electron degeneracy and crushes electrons into protons, creating neutrons. Now it is neutron degeneracy pressure that resists further collapse. The result is a sphere only about 20 kilometers across, yet heavier than our Sun. On its surface, gravity is so immense that a dropped pebble would strike at speeds of tens of thousands of kilometers per second. Its magnetic fields can be trillions of times stronger than Earth's, powerful enough to rip atoms apart. When these stars spin, they sweep beams of radiation across space, creating the pulsars that astronomers detect as rhythmic signals, cosmic lighthouses flashing through the dark. Yet even neutron stars have limits. If the core is too heavy, neutron degeneracy cannot hold, and collapse continues into a black hole. In this final state, space and time bend inward, forming a horizon from which nothing can escape. Black holes are absolute, their interiors hidden from view, their secrets locked away behind a boundary where the known laws of physics cease to function. But the notion of quark stars offers a tantalizing alternative. Between the firmness of neutron stars and the oblivion of black holes may lie another state, born not of electrons or neutrons, but of quarks. If neutrons are squeezed so tightly that their quark components are freed, the star would not vanish into a black hole, but instead stabilize as a sea of quark matter. In this realm, matter is stripped to its most elemental essence, the smallest building blocks revealed under crushing pressure. If quark stars exist, they would sit in the hierarchy of stellar remnants as a hidden fourth category. White dwarfs represent the calm ashes of small stars. Neutron stars are the dense hearts of giants. Black holes are the final abyss. But quark stars would be stranger than any of these, balancing at the edge of collapse, a new state of matter suspended between existence and nothingness. The possibility of quark stars challenges us to rethink the boundaries of physics. They ask whether matter can hold together under pressures far beyond anything in a neutron star. They demand new theories of the strong force. the interaction that binds quarks together inside protons and neutrons. If they are real, they are not only astrophysical objects but messengers from the frontier of quantum chromodynamics, carrying within them secrets that particle accelerators on Earth can only glimpse for fractions of a second. And so, from the simple fusion fires that ignite stars, to the calm of white dwarfs, to the fury of supernova, to the crushing weight of neutron stars, and the finality of black holes, we trace a path that may not end where we once thought. Neutron stars are already among the most extreme forms of matter in existence. Yet the question remains, what if we push even harder? What if neutrons themselves cannot withstand the pressure? What lies beyond? It is here, at this razor edge between collapse and survival, that the idea of quark stars begins. Imagine a star more massive than our Sun collapsing in the final moments of its life. In a blink, its once blazing core shrinks to a sphere no wider than a city, yet it holds more mass than 2 suns. The collapse is halted, not by fusion, not by heat, but by the most stubborn resistance of quantum mechanics. The result is a neutron star, one of the strangest objects in the universe. To grasp what a neutron star is, we must first appreciate its density. On Earth, matter is made mostly of empty space. The nucleus of an atom is tiny compared to the atom itself, and the electrons orbiting it are like dust motes in a vast cathedral. But in a neutron star, all that space is squeezed away. Atoms cannot survive the pressure. Electrons and protons merge into neutrons, and the star becomes one enormous nucleus, a single structure of neutrons packed side by side. Imagine a teaspoon of this material. On Earth, it would outweigh mountains, hundreds of millions of tons compressed into a spoonful. The gravity of such an object is overwhelming. On its surface, gravity is billions of times stronger than on Earth. Drop a pebble, and it would accelerate to a fraction of the speed of light before hitting the crust. Light itself bends dramatically around the star, so much so that we can see parts of its far side at once. The very fabric of space-time is warped into a shape that defies ordinary imagination. Yet despite its crushing gravity, a neutron star does not collapse immediately into a black hole. What saves it is neutron degeneracy pressure. Just as electrons in a white dwarf resist being squeezed together, neutrons resist as well. No 2 neutrons can occupy the same quantum state. This principle of quantum mechanics, invisible in our daily lives, becomes the only thing that prevents total collapse. The star finds balance between the inward pull of gravity and the outward push of degeneracy pressure. And for a time, it endures. But endurance does not mean calm. Neutron stars are restless. They spin at incredible speeds, some rotating hundreds of times each second. As they spin, their intense magnetic fields sweep through space, producing beams of radiation. If these beams happen to cross Earth, we detect them as regular pulses of light or radio waves. These are pulsars, discovered in the 1960s, once thought to be signals from alien civilizations until their true nature was revealed. They are the ticking clocks of the cosmos, keeping time with near-perfect precision. The surface of a neutron star is unlike anything we know. It may be only a few centimeters thick, a crust of nuclei suspended above a sea of superdense neutrons. Underneath, exotic states of matter may exist, including superfluids and superconductors, where particles move without resistance and magnetic fields thread through in strange lattices. Deep in the core, densities may rise so high that even neutrons begin to lose their identity, hinting at a deeper transformation yet to be understood. To picture a neutron star is to imagine the unimaginable. It is an object that compresses entire suns into a sphere no larger than a city. It is a lighthouse flashing across the galaxy. It is a natural laboratory where matter exists in forms beyond the reach of any terrestrial experiment. And it is a threshold, a boundary point in the evolution of stars. For if the pressure grows stronger still, if the crushing weight overcomes even neutron degeneracy, then the neutrons themselves may collapse. Neutron stars already stretch physics to its limits, but the question remains, what if the laws of nature allow one more step? What if the neutrons that compose the star melt into their quark constituents, creating a star stranger still? The answer lies beyond the neutron star's already extreme domain, in the possibility of matter stripped to its deepest essence. Neutron stars are unlike any other object in the cosmos because they exist in a twilight zone between the familiar world of matter and the abyss of black holes. To understand them is to explore what happens when nature pushes matter to a breaking point. If white dwarfs are dense embers and black holes are infinite collapses, then neutron stars are the fragile balance point between the two, hovering on the knife edge of physics. The crust of a neutron star is only the beginning of its strangeness. Just beneath that thin outer skin lies a region where nuclei are squeezed into exotic forms. Protons and neutrons arrange themselves into patterns sometimes called nuclear pasta because their shapes resemble spaghetti strands, lasagna sheets, and gnocchi clusters. These bizarre structures emerge because the competition between nuclear attraction and repulsive forces creates shapes never found in ordinary matter. They may stretch across kilometers, forming a crystalline landscape under unimaginable pressure. Deeper down, nuclei dissolve entirely. Neutrons drip out of their clusters and flow freely, creating a superfluid sea. A superfluid is a state of matter with zero viscosity, meaning it can flow without resistance. On Earth, superfluids exist only under delicate laboratory conditions at temperatures near absolute zero. But inside neutron stars, entire oceans of superfluid neutrons swirl endlessly, immune to friction. Alongside them, superconducting protons thread magnetic fields in quantized tubes, giving neutron stars magnetic powers far beyond anything achievable in human technology. At these depths, strange phenomena appear. Pulsars, for instance, can suddenly change their rotation rates in events called glitches. Astronomers believe these glitches occur when the superfluid interior momentarily transfers angular momentum to the rigid crust, causing the entire star to spin faster. Imagine a city-sized object weighing more than the Sun, suddenly increasing its rotation in a fraction of a second. It is as though the star itself has hiccuped, a reminder that its interior is alive with quantum turbulence. The deeper we descend, the stranger the physics becomes. In the very core of a neutron star, pressures reach beyond nuclear densities. Here, neutrons may be forced into exotic states of matter. Some theories suggest that hyperons, particles containing strange quarks, could emerge, altering the star's structure. Others predict that meson condensates might form, waves of exotic particles coalescing into a single quantum state. Still others propose that at these densities, neutrons themselves dissolve into their constituent quarks, creating a soup of deconfined quark matter. If quark matter does appear, it may not dominate the entire star. Instead, a neutron star might hide a quark core deep inside, surrounded by layers of neutrons and nuclear pasta above. Such hybrid stars would straddle the line between neutron stars and quark stars, offering hints of the transformation without fully committing to it. Detecting these differences, however, is nearly impossible because the star's surface does not reveal its hidden heart. Only by measuring its mass, radius, and cooling behavior can astronomers begin to suspect what lies within. What makes neutron stars so fascinating is that they are not only endpoints of stellar death, but also natural experiments. They test quantum mechanics, nuclear physics, and general relativity all at once. Their gravity warps space-time. Their interiors probe nuclear forces, and their magnetic fields bend plasma in ways no earthbound laboratory can reproduce. They are cosmic crucibles, pressing physics into corners where our equations falter and our theories are stretched thin. Even after decades of study, neutron stars remain enigmatic. Their precise structure is uncertain, their exact composition still debated. Do they harbor quark cores, or do they resist that transformation? Are their surfaces smooth or seething with magnetic storms? Each pulsar signal, each gravitational wave from colliding neutron stars is a clue, a whisper from a realm we cannot visit. Yet all this strangeness leads naturally to a single question. If neutron stars can exist, held together only by degeneracy pressure and the strong force, what happens if we press harder still? Is there a limit where neutrons themselves melt away, revealing the quarks inside? This is the frontier, where neutron stars hand the story to something even stranger, a possible next step in stellar evolution. The story of neutron stars always seems to circle back to one haunting truth. They are survivors, but only barely. Every neutron star sits balanced on the edge of catastrophe, its existence a constant struggle between collapse and resistance. For some, the balance holds for billions of years. For others, the weight is simply too much and gravity claims the prize. To fully appreciate how precarious this balance is, we must look closer at the extreme conditions that define their being. The mass of a neutron star is squeezed into a sphere perhaps 20 kilometers across. The density of such an object is nearly inconceivable. If you could take a cube of neutron star matter the size of a sugar cube and place it on Earth, it would outweigh mountains. Its density is measured not in grams per cubic centimeter, like the familiar materials of daily life, but in billions of tons per cubic centimeter. This is matter pushed to its ultimate limits, where the ordinary rules of atoms no longer apply. In the heart of a neutron star, temperatures at birth soar to hundreds of billions of degrees Celsius. Over time, they cool, radiating energy into space, but their interiors remain hot enough to defy comprehension. Cooling itself is a mystery. Some neutron stars cool quickly, losing heat through the emission of neutrinos, ghost-like particles that slip through matter as though it were transparent. Others cool more slowly, suggesting different physics in their cores. By observing these cooling rates, astronomers hope to glimpse the composition of the star's interior, but the clues are subtle, and the answers remain elusive. The magnetic fields of neutron stars add yet another layer of strangeness. Some possess magnetic fields 1 trillion times stronger than Earth's, while others, known as magnetars, carry fields even 1,000 times stronger still. These magnetic monsters can twist and fracture their crusts, releasing bursts of high-energy radiation that sweep across space. A single outburst from a magnetar can release more energy in a fraction of a second than our sun radiates in hundreds of thousands of years. Such stars remind us that neutron stars are not just passive remnants. They are active, volatile, and sometimes violent. When two neutron stars collide, the consequences ripple across the universe. The merger releases gravitational waves, ripples in space-time itself, first detected by observatories on Earth in recent years. These waves carry information about the structure of neutron stars, about how stiff or soft their matter is, about whether their cores harbor something beyond neutrons. The collision also forges heavy elements, spewing gold, platinum, and uranium into the cosmos, enriching galaxies with the building blocks of planets and life. In these collisions, the fate of neutron stars may also tip into black holes, or perhaps into something even stranger. All of this brings us back to the central mystery. Neutron stars are extreme, but are they the end of the line? If they are pushed further, can they hold together as neutrons, or must they dissolve into something deeper? Theoretical physics suggests that under the most crushing conditions, neutrons cannot remain intact. they will melt into quarks, the fundamental building blocks that compose them. If that happens, the neutron star may not disappear into a black hole, but instead stabilize as a quark star, an object smaller, denser, and stranger than any we have yet confirmed. This possibility turns neutron stars into gateways. They may not only be the strangest objects we know, but also the stepping stones to stranger objects still. If quark stars exist, then every neutron star is a question mark, a candidate teetering between survival and transformation. To study them is to probe not just the death of stars, but the structure of matter itself, right down to the most fundamental particles. And so, as we leave the domain of neutron stars, we find ourselves at a threshold. Neutron degeneracy has resisted gravity's pull, but what if gravity refuses to relent? What if the crushing weight pushes neutrons past their breaking point? The answer lies ahead, in the realm of quarks, where matter is stripped of its familiar form and rebuilt in ways almost beyond imagination. At the very heart of the neutron star, the pressure is beyond description. Here, matter has already been stripped of atoms, electrons have been forced into protons, and the world has become a solid mass of neutrons. Yet even this is not the final word, for neutrons are not fundamental. They are themselves built of smaller pieces, quarks, bound together by the strongest of the forces in nature. Under conditions more crushing than even a neutron star can normally endure, those bonds may finally be broken, and neutrons may dissolve into their quark constituents. Quarks are the foundation stones of matter. Up quarks and down quarks, when combined in threes, form protons and neutrons. They are confined by the strong force, a force so unyielding that quarks cannot be isolated in empty space. On Earth, quarks are always locked inside larger particles, never seen alone. But in the unimaginable depths of a neutron star's core, gravity may supply the pressure needed to overcome this confinement, prying apart the seams of neutrons and spilling their contents into a new state of matter. To imagine this transformation, picture the transition of water from solid ice to liquid to vapor. Each state is different, yet all are made of the same molecules. In the same way, a neutron star's interior may undergo a phase change when density grows too great. What was once a rigid lattice of neutrons could melt into a fluid of free quarks, flowing unbound in a collective sea. This is quark matter, a substance never seen naturally on Earth, but possibly filling the hearts of dying stars. Physicists call this process deconfinement. It is the freeing of quarks from their prison inside neutrons. At first, the change may occur only in the very center of the star, forming a quark core wrapped in neutron layers. But if the star is heavy enough, the transformation could consume the entire object, turning it into something altogether new, a quark star. The line between neutron star and quark star would then be a matter of density and fate, a threshold crossed only under the most severe conditions nature can muster. If this transition occurs, it would be one of the most profound in physics. It would mean that neutron stars are not the ultimate stable state of matter, but only an intermediate step. Beyond them lies a new frontier, where quarks roam free, and where the laws of nuclear physics must be rewritten. The consequences are staggering, for they suggest that the hierarchy of stellar remnants is not threefold, but fourfold, with quark stars standing beside white dwarfs, neutron stars, and black holes. Neutrons, once thought to be the indivisible endpoint of matter in the cosmos, may instead be gateways. And quarks, the unseen particles that shape every atom, may find their own domain not in laboratories, not in equations, but in the hearts of collapsed stars. Quark matter would be stranger than anything we have ever observed, but the logic of stellar collapse leads us here with inevitability. The story of stars is a story of pressure, of matter squeezed to reveal deeper truths. And beyond neutrons, quarks wait. The very thought of quark matter unsettles our sense of reality, for it suggests that the familiar building blocks of atoms are not as immutable as we once believed. If neutrons can collapse into quarks, then what we regard as stable matter is only a fragile arrangement, waiting to be unraveled under sufficient pressure. In the cores of neutron stars, densities may reach several times greater than those found inside atomic nuclei. At that scale, the quarks that were once confined in neat trios within neutrons begin to spill out, merging into a sea where individuality is lost. This quark sea is thought to behave in ways utterly alien to us. Instead of separate protons and neutrons, the matter may become a collective fluid of up and down quarks, possibly joined by strange quarks if the conditions are right. These strange quarks, heavier cousins of the ordinary up and down, might stabilize the matter even further, leading to what theorists call strange quark matter. If such matter is more stable than ordinary nuclear matter, it could form entire stars, and in principle, even fragments of it could persist as strangelets, tiny nuggets of exotic substance drifting through the cosmos. Unlike the rigid crust and layered structure of a neutron star, a quark star would be smooth and uniform throughout. Its surface might be bare, without atoms or nuclei to form an atmosphere, instead exposing the raw quark matter itself. Light emerging from such a surface would not resemble the thermal radiation of ordinary stars. It might appear unusually hard, with spectral properties that defy easy classification. For astronomers searching for quark stars, these peculiar signals are the fingerprints they hope to find. The physics of such a state is tied to one of the most fundamental theories in science, quantum chromodynamics, the theory of the strong force. On Earth, we probe quark matter fleetingly in particle accelerators, smashing atomic nuclei together at nearly the speed of light to create tiny droplets of quark gluon plasma. These droplets exist for only the briefest moments, less than a trillionth of a second, before cooling back into ordinary particles. In the heart of a quark star, however, the quark matter could persist indefinitely, stabilized by gravity and pressure. To step from neutrons into quarks is to cross a frontier. It is not merely denser matter, but matter in an entirely different phase. It is as if the universe has peeled back a deeper layer of reality, revealing a hidden form of existence that we can never touch with our hands, but only infer from the signals of distant stars. Neutron stars already press against our imagination, but quark stars would push beyond, into a realm where the familiar categories of matter dissolve. This transformation is not certain. We cannot say with confidence that it occurs, only that the laws of physics suggest it might. The equations of quantum chromodynamics are notoriously complex, and even the most advanced supercomputers struggle to solve them at the densities found in stellar interiors. Yet the possibility remains, hanging over our understanding of stellar death like a challenge. If nature allows quark matter to form, then neutron stars are not endpoints at all. They are merely doors, and behind those doors lies a stranger room than we have yet dared to imagine. At the edge of neutron stars, then, we find more than just physics. We find a story that hints at the unfinished nature of our knowledge. Each step deeper, from atoms to nuclei, from nuclei to neutrons, from neutrons to quarks, is a descent into smaller and smaller building blocks. Each step changes the rules, as though the universe keeps hidden layers waiting to be revealed when the pressures grow high enough. If neutron stars show us matter at its most compressed familiar state, quark stars would reveal matter stripped to its essence, reduced to the purest constituents of all. At the threshold between neutrons and quarks lies one of the most tantalizing mysteries in astrophysics. Neutron stars already defy the ordinary, yet if the crushing weight inside them pushes further, their very nature may unravel. Neutrons, no longer able to remain whole, dissolve into a new form of matter where quarks roam free. This is not simply denser material, it is a shift as profound as the change from solid to liquid, from liquid to gas, or even beyond. It is a transformation of the very fabric of matter. If such a transition occurs, it would not be gradual. Physics suggests that when pressures rise beyond a critical threshold, neutrons collapse almost suddenly, and their quark components flood outward in a chain reaction. A neutron star could, in principle, transform into a quark star in a matter of moments. The collapse would release enormous amounts of energy, perhaps enough to create bursts of gamma rays, the most powerful explosions known in the universe. These cosmic flares may already have been seen, though their true origin remains uncertain. The existence of quark stars would also mean that the line we draw between neutron stars and black holes is not sharp, but blurred. Some collapsing stars, instead of vanishing into black holes, might stabilize as quark stars, teetering on the edge of oblivion, but refusing to fall. Their radii would be smaller than neutron stars of the same mass, their densities even higher, but they would not yet be swallowed by their own gravity. They would occupy a hidden niche in the spectrum of stellar remnants, more compact than neutron stars, less final than black holes. Quark stars would not only be objects of astrophysical curiosity, they would also be windows into fundamental physics. On Earth, quark gluon plasma is glimpsed only for fractions of a second in colliders, but in quark stars, it might exist stably for millions or billions of years. Observing such objects, if we can confirm them, would allow us to test theories of the strong force in conditions beyond any laboratory. It would be as though the universe had built us an experiment and set it spinning in the sky. Astronomers searching for quark stars look for hints in the light of unusual pulsars and compact stars whose properties do not quite match those of ordinary neutron stars. A star that is too small for its mass, or that cools faster than theory predicts, might be a candidate. Signals that deviate from the expected behavior of neutron stars may betray the presence of quark matter hidden within. Yet confirmation remains elusive, for the differences are subtle, and the cosmos does not easily give up its secrets. Still, the logic of collapse leads us here. From atoms to nuclei, from nuclei to neutrons, and from neutrons to quarks, the path is one of ever deeper compression, ever higher densities, ever stranger forms. To stop at neutron stars is to leave the story unfinished. The possibility of quark stars beckons us onward, promising a new chapter in the saga of stellar death, a chapter stranger than any before. And so, from the life and death of stars, through the crushing weight of neutron stars, we arrive at the threshold of the unknown. What would a star made entirely of quark matter look like? How would it shine? How would it live? How would it die? The next step in our journey takes us into this uncharted territory, where the hypothesis of quark stars becomes more than speculation, where theory meets the challenge of reality. To imagine a quark star is to imagine matter stripped to its most elemental form. Neutron stars already push matter to a state beyond ordinary imagination, squeezing atoms until electrons and protons fuse into neutrons. But a quark star would go further, crushing those neutrons themselves until their internal quarks are freed. The result would be an object unlike any other, a star composed almost entirely of quark matter, a sea of fundamental particles bound not by nuclei, but by the barest threads of the strong force. In such a star, there would be no atoms, no nuclei, no neutrons. Instead, up quarks, down quarks, and possibly strange quarks would swirl in a collective fluid, forming a phase of matter that cannot be recreated on Earth except for fleeting instants in particle accelerators. If strange quarks are present, the star may be called a strange star, a name given because strange quark matter could be more stable than ordinary nuclear matter. In this scenario, quark stars are not only possible, but inevitable. For once the threshold of density is crossed, the collapse into quark matter becomes unavoidable. Quark stars would share certain traits with neutron stars, for both are born in the violent deaths of massive suns. Their sizes would be comparable, only tens of kilometers across, but the details would set them apart. A quark star of a given mass would be smaller than a neutron star, for quark matter is more compressible. Its surface would not be composed of a solid crust of nuclei, but may instead be a bare expanse of quark matter itself, with strange properties unlike anything known. Light escaping such a surface might appear unusual, perhaps harder or smoother than from a neutron star. The difference would be subtle but detectable, a fingerprint of the quark sea beneath. The physics within such a star would be alien. Quark matter might exist in states with exotic names like color superconductivity, where quarks pair up in ways reminiscent of electrons in superconductors, flowing without resistance. The interior of a quark star might be layered with phases of quark matter, each with different arrangements of quarks and gluons, each stable only at certain pressures and temperatures. What we think of as matter may become a spectrum of possibilities, shaped by conditions found nowhere else but in these stars. To call such objects stars is almost misleading. They would no longer shine with the fusion fires of hydrogen or helium. Their light would be the fading glow of their formation, the residual heat of collapse, the radiation of particles escaping their dense cores. They would be dark embers of quark matter, glowing faintly across the void, as much the tombstones of suns as the neutron stars they replace. And yet, in their quietness, they would be more radical than any fusion-powered star, for they would embody a state of matter that rewrites our understanding of physics. Neutron stars already stretch our imagination, but quark stars would demand we abandon familiar categories altogether. They would be proof that the hierarchy of stellar remnants is richer than we believed, that the universe hides deeper layers of matter than we ever suspected. Their existence would mean that stars can end not in 3 ways, but in 4, with white dwarfs, neutron stars, quark stars, and black holes marking the stages of collapse. But the question remains unanswered. Do quark stars truly exist, or are they only theoretical phantoms, glimpses of what could be but never is? The search for them drives astronomers to examine the faintest signals from distant pulsars, to compare cooling curves, to measure masses and radii with exquisite precision. Only by finding deviations from neutron star predictions can we claim to have found one of these exotic objects. Until then, they remain an open question, a possibility lingering at the edge of science. Neutron stars are extreme, but quark stars would be stranger still. They invite us to ask whether nature has already created them, hiding in plain sight among the pulsars and compact stars we have catalogued. The universe may already contain these hidden laboratories, waiting for us to recognize them. The next step in our journey then is to seek evidence, to search the skies for the telltale signs that quark stars are real. Quark stars are not merely compact objects. They are thought experiments made flesh, possibilities that strain our imagination and challenge our physics. If they exist, their interiors would host forms of matter that until now have only been hinted at in equations and in fleeting laboratory experiments. Unlike neutron stars, which preserve neutrons as the dominant building blocks, quark stars would represent the next descent into substructure, the liberation of quarks themselves into a collective medium. In this vision, the star may not be a uniform soup, but a layered body of exotic states. The outer layers could still resemble those of neutron stars, but beneath them, quark matter would appear in phases no less strange than those we imagine for superfluids and superconductors. One possibility is that the quarks, though free, would pair up in ways that mirror the behavior of electrons in superconductors. This so-called color superconductivity would mean that quarks flow without resistance, locked together in collective bonds shaped by the strong force. In such a state, the interior of a quark star would be silent, frictionless, perhaps threaded by quantized fields unlike anything we know. Among the most fascinating prospects is the emergence of strange quarks, heavier cousins of the familiar up and down quarks. If conditions permit, these strange quarks could join the sea, stabilizing the matter further and creating what is called strange quark matter. If strange quark matter is more stable than ordinary nuclear matter, then the implications ripple outward. Not only could entire stars be made of this substance, but fragments might drift as strangelets, tiny nuggets that, if they encountered normal matter, could in theory convert it to their own form. Such an idea borders on the philosophical, raising questions about whether our universe has always harbored these seeds of transformation. From the outside, a quark star would look superficially similar to a neutron star, a small sphere only tens of kilometers wide. But its surface might betray its identity. Some models suggest a bare quark surface, smooth and featureless, with light emitted directly from the quark matter beneath. Others propose a thin crust of normal matter clinging to the star, only meters thick, supported by the strong electric fields of the quark core. Either way, its radiation would differ subtly from that of neutron stars, perhaps in its spectrum, perhaps in the way it cools. For astronomers, these differences would be the faint signals by which to tell the two apart. In their very existence, quark stars would expand our understanding of nature. They would be cosmic laboratories of the strong interaction, places where quantum chromodynamics is not just a theory scribbled in equations, but a physical reality shaping stars. They would be the first stable, large-scale structures of quark matter, existing not for fractions of a second, but for ages. They would be reminders that the universe is not limited to the familiar, that beneath every layer lies another, waiting for pressure and gravity to expose it. And yet, the grandest question still lingers. We can imagine them, describe them, even predict their properties, but do they exist? This is the mystery that propels astronomers to search for anomalies among pulsars, to measure compact stars with precision, to test every unexplained behavior against the possibility of quark matter. It is the mystery that makes quark stars more than theory, it makes them a frontier. Quark stars occupy a peculiar place in our imagination, balanced between theory and reality, between speculation and discovery. They are built on solid physics, yet they have never been confirmed. And so we are left to weigh their predicted properties against the signals we can measure from the sky, always asking whether the data we gather is whispering of something beyond neutrons. A neutron star, dense as it is, has a definite relationship between its mass and radius. The more massive it becomes, the smaller it must be. But this shrinking has limits. If we measure a compact star that is too small for its mass, it may already be beyond the neutron star limit, pointing to quark matter within. Quark stars should be more compact than neutron stars of the same mass, their radii perhaps 10 kilometers or even less, and this difference is a crucial signature. Astronomers use X-ray observations, thermal emissions, and pulsar timing to infer these parameters, searching for anomalies that could reveal quark stars hidden among their cousins. The way a star cools is another clue. Neutron stars radiate heat over millions of years, and their cooling rates follow predictable models tied to the behavior of neutrons and protons. But if quark matter fills the interior, the cooling could proceed faster, driven by more efficient neutrino emission from quark processes. A star that fades quicker than theory allows may be betraying its quark heart. Likewise, magnetars, with their bursts of energy, could hold hints of quark matter releasing energy in sudden transformations. Even rotation may hold secrets. Neutron stars spin with remarkable regularity, but as we have seen, they sometimes glitch. A quark star with its smoother and more fluid interior might glitch differently, or perhaps not at all. If one day we detect a pulsar whose timing anomalies cannot be explained by neutron models, we may be staring at the evidence of quark matter. Yet the challenge is immense, the differences are subtle, and the cosmos is noisy. Observational uncertainties blur the line between neutron and quark stars, leaving astronomers cautious. We have candidates, compact stars whose properties are unusual, whose radii seem too small, whose cooling is too rapid. But caution rules science, and until the evidence is undeniable, the existence of quark stars remains hypothesis. Still, the idea persists because it is not a fantasy, but an extension of the very physics that explains neutrons themselves. To deny the possibility would be to deny the logic of compression, the inevitability of deeper phases of matter under greater pressures. If the universe creates neutron stars, why should it not also create quark stars? Perhaps they are rare, born only in the most massive collapses, or perhaps they are common, hiding among pulsars, indistinguishable until our instruments grow sharper. We leave this chapter with the question still hanging. Neutron stars are real, black holes are real, white dwarfs are real, but quark stars linger at the threshold between what we know and what we suspect. They are the next rung on the ladder of stellar remnants, the next natural step in the story of collapse. The question is not only whether they exist, but whether we have already seen them without recognizing their true nature. And so we turn to the next part of our journey, to the search for evidence. If quark stars are out there, hidden among the remnants of stellar death, we must learn how to find them. The hunt begins with anomalies, with outliers, with stars that do not fit the mold. It begins with the sky itself, whispering of possibilities stranger than neutron stars. Astronomers have long suspected that the cosmos may be hiding objects stranger than neutron stars, and for decades they have searched the skies for proof. If quark stars exist, they would not look dramatically different from neutron stars at first glance. Both would be compact remnants only tens of kilometers across. Both would shine faintly with the fading heat of their collapse, and both might appear as pulsars if their magnetic beams sweep across Earth. The challenge lies in the subtle differences, the whispers in the data that hint at something more exotic. One of the earliest candidates came in the form of RxJ 1856.5-3754, a nearby compact star observed in X-rays. Its thermal spectrum was unusually smooth, lacking the absorption lines expected from a neutron star atmosphere. Some researchers suggested that this might mean it had no conventional surface at all, but instead a bare quark matter surface. Though other explanations, such as unusual atmospheres or magnetic effects, remain possible, RxJ 1856 became one of the first serious hints that quark stars might not just be theory. Another curious object is the pulsar in the supernova remnant 3C58. Its measured temperature appeared far lower than standard cooling models for neutron stars could explain. If the star were made of quark matter, however, it could cool more efficiently through quark-level processes, releasing neutrinos at a far greater rate. This mismatch between observation and prediction opened the door to the idea that 3C58 might be a quark star masquerading as an ordinary pulsar. The search does not stop with individual stars. Astronomers also look to gravitational wave signals from neutron star mergers. When two neutron stars collide, the resulting remnant may briefly survive before collapsing into a black hole. The way it vibrates and sheds gravitational energy encodes information about the stiffness of matter inside. If quark matter forms during the collision, the gravitational wave signature could change dramatically, leaving a detectable fingerprint. Already, the events recorded by detectors have begun to test these possibilities, and future observations promise to sharpen the picture further. Mass and radius measurements are another battleground. A neutron star of 2 solar masses has been confirmed, placing strict limits on how soft or exotic its interior can be. Yet if astronomers find a star smaller than theory allows for its mass, it could point to quark matter compressing the star beyond neutron models. The precise relationship between mass and radius, measured by timing pulsars and analyzing X-ray bursts, may be the most decisive test. But the measurements are challenging, plagued by uncertainties that leave room for interpretation. Hunting for quark stars is, in essence, an effort to find anomalies. It is the search for stars that do not fit the mold, whose temperatures, radii, or signals diverge from what neutron stars should display. Each anomaly could have other explanations, yet together they weave a story of possibility. Perhaps the universe has already revealed quark stars to us, and we are only now learning how to recognize them. But if the evidence remains elusive, what would it take to prove their existence beyond doubt? Could we one day detect the unique light of a bare quark surface, or the sudden transformation of a neutron star into a quark star, a process that might erupt as a gamma ray burst? Could gravitational wave observatories catch the moment when neutrons melt into quarks in the heart of a merger? These are the questions driving astronomers, who know that proof may come not from a single observation, but from a convergence of signals across many instruments. The hunt continues, sharpening with every new telescope, every new detector, every new burst of light from the cosmos. Quark stars, if they exist, will not hide forever. And if we find them, the discovery will not only confirm a new class of stellar object, it will rewrite our understanding of nuclear physics itself. The search for quark stars has often been described as a detective story, a chase through the cosmos for suspects that do not quite match their expected profiles. Each candidate is a puzzle piece, a clue that may point toward a deeper truth, or may dissolve under closer scrutiny. Astronomers must tread carefully, because the line between neutron stars and quark stars is subtle, and other explanations can often mask themselves as the extraordinary. Take again the case of RxJ 185.6.5-3754. Its lack of spectral lines was tantalizing. A bare quark surface could explain the smooth spectrum, yet alternative models argue that strong magnetic fields could strip away or blur the features we expected to see. Even so, the object remains a prime suspect, an outlier that refuses to be explained away completely. The pulsar in 3C58 presents another riddle. Cooling too quickly for neutron star theory, it has tempted scientists to invoke quark matter, which would vent energy through more efficient neutrino processes. But critics note that uncertainties in age and environment might also account for the anomaly. The candidate remains intriguing but inconclusive, a shadow on the boundary between theory and observation. Other compact stars continue to deepen the mystery. Some have been measured with radii so small that they strain the neutron star equation of state, the relation that describes how matter behaves at extreme densities. If confirmed, such stars could be prime evidence for quark interiors. Yet measurements of mass and radius in such distant objects are difficult, and the data often leaves room for error. A few kilometers of uncertainty can mean the difference between a neutron star and a quark star. The gravitational wave era has opened a new window. When two neutron stars spiral together and merge, the signal they produce depends on how deformable they are under tidal forces. A star made of quark matter would squish differently than a star made only of neutrons, leaving faint but measurable differences in the wave pattern. Already, events like the merger seen in 2017 have given astronomers the first glimpses of such effects, though the data is not yet precise enough to draw firm conclusions. The hope is that as detectors improve, the fingerprints of quark matter will emerge clearly in the cosmic symphony of merging stars. Even pulsar timing has a role to play. Millisecond pulsars, which rotate hundreds of times each second, can be measured with exquisite precision. If one of them were to undergo a sudden transformation from a neutron star to a quark star, its spin would change in a measurable way. Some researchers have speculated that unexplained irregularities in pulsar timing might be signatures of such transitions, though again, the evidence remains circumstantial. Each candidate and each method carries uncertainties, yet together they create a growing tension. Too many anomalies press at the edges of neutron star theory. Too many signals hint at matter beyond neutrons. It may be that we are already looking at quark stars, but without the tools to confirm them with certainty. In the coming years, new instruments like the Square Kilometre Array and next-generation gravitational wave observatories may finally deliver the precision needed. Until then, the hunt for quark stars is as much about refining our theories as it is about making new discoveries. Every anomalous pulsar, every unusual cooling curve, every merger signal forces theorists to sharpen their models of matter under pressure. And in that sharpening, we edge closer to clarity. If quark stars exist, we will find them. And when we do, the implications will reach far beyond astronomy, into the heart of nuclear physics itself. The evidence for quark stars hovers always at the edge of certainty, just out of reach. Each new observation sharpens the picture, yet each also leaves enough room for alternative explanations. This is the nature of science at the frontier, where instruments strain against their limits and where nature's signals arrive faint and complex across the gulfs of space. To prove the existence of quark stars would require more than a curious spectrum or an unusual cooling curve. It would require converging lines of evidence, each pointing to the same conclusion. A mass and radius that cannot fit within neutron star theory, a cooling rate that matches quark predictions, a gravitational wave signal that reveals quark-level deformability. Together, these would build a case too strong to deny. The goal is not one piece of evidence, but a constellation of them, each reinforcing the others until the picture is undeniable. The challenge is compounded by the fact that neutron star physics itself remains uncertain. We do not yet know with absolute precision how matter behaves at several times nuclear density. Equations of state vary, predictions differ, and small changes ripple into large uncertainties. To claim a quark star, then, is also to claim a mastery of neutron star theory we do not yet possess. It is a puzzle within a puzzle, requiring us to solve both the known and the unknown at once. Still, the possibility is too important to ignore. If quark stars are real, they are not just another kind of stellar remnant. They are keys to the strong interaction, the force that binds quarks inside protons and neutrons, the force that defines the structure of matter itself. They would offer insights into quantum chromodynamics at densities impossible to test on Earth. They would connect the deaths of stars with the deepest laws of particle physics, binding the cosmos and the quantum in a single story. And so, the hunt goes on, driven not only by curiosity, but by the promise of revelation. Each telescope, each detector, each analysis of pulsar timing or X-ray emission is another step closer. The candidates remain intriguing, the anomalies compelling. Perhaps the next observation will tip the balance, or perhaps years more will pass before certainty arrives. But when that day comes, when we confirm that quark stars walk the line between neutron stars and black holes, it will be a turning point in science. For then, we will know that matter, under the most extreme pressures of the universe, takes forms stranger than anything seen on Earth. We will know that stars do not simply end as white dwarfs, neutron stars or black holes, but that some transform into quark stars, the strangest stellar corpses of all. And in that knowledge, nuclear physics itself will be rewritten, for the quark star will not only be an astronomical discovery, but a fundamental one, reshaping how we see matter at its most basic level. The question of their existence is not just about stars. It is about whether the universe holds deeper layers of truth than we have yet revealed. To find quark stars is to prove that the cosmos contains realms beyond our imagination, waiting only for us to develop the vision to see them. The idea of quark stars cannot be separated from the physics of quark matter itself. To ask whether such stars exist is to ask whether quark matter can be stable on cosmic scales, and to answer that question, we must descend into the foundations of the strong force, the most powerful interaction in nature. The strong force binds quarks into protons and neutrons, and binds those protons and neutrons into atomic nuclei. Unlike gravity or electromagnetism, the strong force does not weaken with distance in the same way. Instead, it grows stronger as quarks are pulled apart, like a rubber band that stretches tighter the more you tug on it. This is why quarks are never seen alone. Try to pull one free, and the energy in the stretched bond simply creates new pairs of quarks, which immediately lock themselves into particles. This confinement is why every atom in the universe exists. Yet paradoxically, at extremely high energies or densities, the strong force weakens. This phenomenon is called asymptotic freedom. When quarks are pressed close together, or when they collide at near light speeds in accelerators, their bonds loosen and they can behave almost like free particles. This counterintuitive feature of the strong force lies at the heart of quantum chromodynamics, the theory that describes how quarks and gluons interact. On Earth, we glimpse this freedom only for fleeting instants. In colliders such as those at CERN and Brookhaven, atomic nuclei are smashed together at near light speed, creating tiny droplets of quark-gluon plasma. These droplets exist for less than a trillionth of a second, reaching temperatures of trillions of degrees Celsius, hotter than anything since the birth of the universe. In those moments, quarks move almost freely, revealing their properties in sprays of particles detected around the collision. These experiments confirm the theory, but they cannot create stable quark matter. The droplets are too small and too hot to endure. A quark star would be a natural laboratory where this quark matter exists stably for millions or even billions of years. Unlike the searing plasma in colliders, the quark matter in such a star would be cooled by time and bound by gravity, forming a condensed phase rather than a fleeting explosion. Instead of droplets that evaporate instantly, the star itself would be a vast reservoir of deconfined quarks, persisting on cosmic timescales. The difference between quark matter in accelerators and in stars is not only temperature but also scale. In colliders, quarks emerge in tiny, chaotic volumes, too small to settle into new phases. In a star, however, the sheer size and density allow quark matter to organize, perhaps into stable states such as color superconductivity, where quarks pair in patterns that minimize energy, flowing without resistance. These are not metaphors, but literal phases of matter, predicted by theory, but beyond direct human experiment. Thus, the physics of quark matter bridges the smallest and the largest, the laboratory and the cosmos. In one domain, we smash nuclei together for fractions of a second to glimpse quarks. In the other, stars collapse under gravity to create conditions where quarks may remain free forever. The universe itself becomes the experiment, and quark stars the evidence that nature explores realms far beyond what we can build with machines. If quark stars exist, they are not just astronomical oddities. They are confirmations of deep theoretical truths, living monuments to the strong force and its paradoxical behavior. They would link the quantum with the cosmic, showing us that the rules written in the language of quarks and gluons govern not only the insides of protons, but the fate of dying suns. In laboratories on Earth, the closest we come to quark matter is the fleeting creation of quark-gluon plasma. This exotic state was first confirmed in the early years of the 21st century, when colliders smashed heavy nuclei together at immense energies. For the briefest moments, the collisions melted protons and neutrons, freeing their quarks and gluons into a tiny fireball hotter than the core of any star. In that fireball, Quarks no longer confined themselves to trios, but roamed in a collective plasma, interacting through color charges carried by gluons. Color charge is the fundamental property of quarks in the same way that electric charge is the property of electrons. But while electricity is governed by one type of charge, positive or negative, the strong force recognizes three types of color charge. These colors are not literal, but names given to the mathematical labels red, green, and blue. Gluons, the force carriers, shuffle color between quarks, ensuring that only color-neutral combinations survive in isolation. In ordinary matter, this confinement locks quarks into protons and neutrons, but in quark-gluon plasma, the rules relax. The quarks and gluons swirl together freely, their colors mixing in a collective storm. The plasma created in colliders is extraordinary, yet it is also ephemeral. It expands, cools, and freezes back into ordinary matter almost instantly. What is remarkable is how this plasma behaves. Instead of acting like a thin gas of free particles, it flows like a nearly perfect liquid, with almost no viscosity. The collective motion of quarks and gluons in these collisions revealed a new face of matter, one that is still being explored in theory and experiment. In a quark star, the situation would be radically different. Instead of a fireball of quarks expanding into nothing, the quark matter would be held in place by gravity and cooled by time. Instead of trillions of degrees, the interior might be only millions, still hot by human standards, but far cooler than the collider's plasma. The star's enormous scale would allow the quark matter to settle into phases unknown on Earth, phases predicted but never observed. One such phase is color superconductivity, where quarks form pairs bound by the strong force, creating currents with no resistance. Another possibility is crystalline color superconductivity, where quarks arrange themselves in repeating patterns, a kind of cosmic lattice woven from the smallest particles. These differences mean that the quark matter in stars is not the same as the plasma glimpsed in accelerators. They are two manifestations of the same fundamental theory, quantum chromodynamics, but under different conditions of temperature and density. One is hot and ephemeral, the other cold and eternal. To study both is to map the full phase diagram of matter, from the fireball of the Big Bang to the quiet cores of collapsed stars. The fact that quantum chromodynamics allows for such diversity of states underscores the richness of the strong force. Unlike electromagnetism, which produces familiar phases like solids, liquids, and plasmas, the strong force admits far stranger possibilities, from baryons and mesons to quark matter and color superconductors. The cosmos, with its collapsing stars, may be the only place where these possibilities are realized on stable, macroscopic scales. If we confirm quark stars, we will have found not just new astronomical objects, but a new form of matter. We will have uncovered a realm where the building blocks of atoms behave in collective ways, where the smallest scales shape entire stars. In doing so, we would connect the work of particle physicists on Earth with the evolution of the universe itself, showing once again that the very large and the very small are bound together by the same laws. The bridge between astrophysics and quantum chromodynamics is more than metaphor. It is a direct connection between the laws governing quarks and the lives of stars. Neutron stars are already extraordinary because they unite gravity, quantum mechanics, and nuclear physics in one object. But quark stars would go further, demanding that we confront the full machinery of the strong interaction on a cosmic scale. In particle accelerators, quantum chromodynamics is tested in the regime of high temperature and low density. Here, collisions recreate a microcosm of the early universe, when matter existed as a hot quark-gluon plasma, only microseconds after the Big Bang. In the cores of quark stars, however, the conditions are reversed. The temperature is lower, but the density is so high that neutrons dissolve. This is the high-density, low-temperature corner of the phase diagram, inaccessible to experiments on Earth. By observing quark stars, we would probe this uncharted domain, completing the map of matter under extremes. This map is not just academic. It tells us how the universe behaved in its earliest moments and how it behaves in its most violent deaths. The transition from neutrons to quarks in collapsing stars echoes the transition from quarks to hadrons in the infant universe. One is a star dying, the other a cosmos being born, yet both are bound by the same physics. To glimpse a quark star would be to glimpse the conditions of creation itself, preserved in the hearts of dying suns. The importance of such stars, if they exist, cannot be overstated. They would confirm that the strong force is not just a detail of nuclear physics, but a shaper of cosmic history. They would show that the same equations describing quarks inside a proton also decide the fate of collapsed stars, binding together the smallest scales with the largest. They would remind us that physics is one story, stretching from the laboratory to the galaxy, from the smallest particle to the grandest explosion. And so, the physics of quark matter is not confined to equations or colliders. It is written across the sky in the remnants of stars, in the flicker of pulsars, in the ripples of space-time from colliding neutron stars. To find quark stars would be to complete the circle, uniting what we have glimpsed in accelerators with what nature builds on cosmic scales. It would mean that the laboratory of the universe is far larger, far stranger, and far richer than we had imagined. This is why the search matters. Quark stars, if real, are not just another category in the taxonomy of stellar corpses. They are the key to linking astrophysics and quantum chromodynamics, to proving that the physics of quarks does not end at the boundaries of nuclei, but extends to the very cores of stars. They would show that the story of collapse is not finished at neutron stars, but continues into realms stranger still. And so, having traced the physics of quark matter, we now turn to the consequences. If quark stars exist, what role do they play in the universe? What dangers and wonders might follow from their stability? Could they spread strange matter across the cosmos, infecting neutron stars and transforming them into quark stars? Could their collisions shape the signals we see as gravitational waves, or seed the universe with new elements? These are the cosmic consequences, and they lead us deeper still into the mystery. If quark stars exist, their significance reaches far beyond classification. They would not merely expand the catalogue of stellar remnants, they would raise profound questions about the stability of matter itself. For if strange quark matter is more stable than the neutrons and protons that make up ordinary matter, then the existence of even a single quark star would imply a potential chain reaction, a quiet but inexorable transformation spreading across the cosmos. This idea, sometimes called the strange matter hypothesis, suggests that strange quark matter may be the true ground state of matter, more stable than ordinary nuclei. In that case, neutrons and protons are only metastable, persisting not because they are unbreakable, but because they require extreme conditions to fall into their lower energy form. If so, then a quark star is not just a curiosity, but a warning, a reservoir of matter that could in principle convert anything it touches into its own kind. Imagine a neutron star drifting too close to a quark star. As soon as a fragment of strange matter makes contact, it could begin converting neutrons into quarks, spreading like a contagion through the star. In a matter of moments or years, depending on the models, the entire neutron star could collapse into quark matter, becoming a new quark star in turn. If this is true, then once the universe produces one quark star, the process may continue, transforming neutron stars into quark stars across cosmic time. The possibility is both terrifying and fascinating. On the one hand, it raises the spectre of strangelets, small nuggets of quark matter that might drift through space, converting anything they touch. On the other, it offers a mechanism by which the universe might naturally regulate the balance of stellar remnants, ensuring that neutron stars are only a temporary phase. In either case, the consequences are enormous. This transformation might even leave traces we can observe. A neutron star collapsing into a quark star would release a burst of energy, perhaps in the form of gamma rays or neutrinos. Some unexplained gamma ray bursts could, in theory, be the signatures of such conversions. The sudden change in radius and structure might also send gravitational waves rippling outward, detectable by sensitive observatories on Earth. If such signals are ever identified, they would not only confirm quark stars, but reveal the process by which they spread. The strange matter hypothesis remains unproven, and many physicists caution that it may be more speculation than reality. Yet the idea is not easily dismissed, for it arises directly from the equations of quantum chromodynamics. If strange quark matter is indeed the true ground state, then the cosmos itself has already decided the outcome. Neutron stars would not endure forever. They would eventually yield to the deeper stability of quark stars, whether in isolated collapses or in a wave of conversions rippling through the galaxies. Even without contagion, the existence of quark stars would have vast consequences. Their collisions would differ from those of neutron stars, producing gravitational wave signatures that carry the imprint of quark matter. Their cooling patterns would shape the radiation we detect in X-rays. Their very presence would shift the landscape of compact objects, demanding new models for how stars die and what remnants they leave behind. Quark stars, then, are not passive curiosities. They are active participants in the cosmic drama, with the power to reshape the physics of collapse, the dynamics of mergers, and even the fate of neutron stars themselves. To find them is to uncover not only a new kind of star, but a new force in the evolution of the universe. If quark stars are real, their influence on the cosmos would be written into some of the most spectacular events in the universe. When two neutron stars collide, the aftermath is an explosion of light and energy known as a kilonova. These collisions have been confirmed to forge the heaviest elements in the periodic table, scattering gold, platinum, and uranium into the interstellar medium. But if one or both of the stars involved are quark stars, the outcome may be very different. A neutron star merger begins as a gravitational dance, two dense remnants spiraling closer as they radiate away energy in the form of gravitational waves. In the final moments, the stars tear at each other with tidal forces strong enough to disrupt their outer layers. What happens next depends on the physics of matter at nuclear and supranuclear densities. If quark matter is present, it can change the entire sequence of events. A star with a quark core may collapse more quickly, or may briefly stabilize in a hybrid configuration before falling into a black hole. The resulting gravitational wave signal would carry subtle differences, tiny shifts in frequency and amplitude that reveal the stiffness of matter deep inside. Detecting these shifts would be like hearing quark matter sing in the cosmic symphony of space-time. The light that follows such mergers could also carry the imprint of quark matter. In ordinary kilonovae, neutron-rich debris is flung outward, where it undergoes rapid nucleosynthesis, creating heavy elements. But if quark matter is involved, the composition of the ejector may differ. Strange quarks could alter the balance of particles, changing the chemical makeup of what is cast into space. The light curves, the way the explosion brightens and fades, could deviate subtly from expectations. Already, astronomers are refining their models to see whether some of the kilonovae observed in recent years hint at quark involvement. Even more dramatic is the possibility of a direct transition. If a neutron star is on the edge of stability, a collision might trigger the collapse of its core into quark matter. The sudden conversion could release a flash of energy, a brief but intense burst that would superimpose itself on the gravitational and electromagnetic signals. Some scientists speculate that certain short gamma-ray bursts might be explained by such transitions, though the evidence is still circumstantial. Beyond collisions, quark stars could also influence isolated phenomena. A lone neutron star that gradually cools and contracts might someday reach the threshold of quark formation, collapsing suddenly into a quark star. Such an event would be violent, releasing energy in neutrinos, light, and possibly gravitational waves. If observed, it would be one of the most decisive confirmations of quark matter in the cosmos. These scenarios remind us that quark stars, if they exist, are not static curiosities. They would shape the behavior of mergers, the distribution of heavy elements, the character of gamma-ray bursts, and the very signals we use to map the universe. Their fingerprints would be found in the faint ripples of space-time and in the brilliant light of exploding stars. The consequences extend even further into the story of cosmic evolution. Heavy elements are essential for planets and life, and if quark matter alters their production, then quark stars would play a hidden role in shaping the environments where life emerges. The fate of galaxies, the chemistry of worlds, the richness of the periodic table, all may bear the quiet mark of quark stars. If we prove they exist, then every gravitational wave detection, every kilonova, every anomalous pulsar becomes a chance to learn not only about stellar remnants, but about the deep laws of nature. The cosmos would no longer be divided neatly into neutron stars and black holes, but would reveal a richer spectrum of fates. And in that spectrum, quark stars would occupy a place of immense consequence, both for astrophysics and for the story of existence itself. The thought that quark stars might exist forces us to reconsider not just astrophysics, but the very philosophy of matter. If strange quark matter is more stable than the protons and neutrons that make up our bodies, then ordinary matter is not truly fundamental. It is only a temporary arrangement, a fragile balance that endures under ordinary conditions, but that collapses when pushed to extremes. In that sense, our world may be built not on the ground state of matter, but on a plateau above it, safe only because the universe does not often press down hard enough to reveal what lies below. If quark stars form, they reveal that this hidden ground state is real, that matter prefers a deeper, stranger arrangement. And if that is true, then it raises unsettling questions. Could a fragment of strange quark matter, drifting through space as a stranger lay, transform the world it touches? Could entire neutron stars be doomed to eventual conversion, their stability only temporary in the face of the universe's relentless search for equilibrium? The possibility has inspired both scientific papers and philosophical debates, for it challenges the assumption that the matter we see around us is permanent. It is possible that such fears are misplaced, that strange quark matter is not stable enough to spread beyond its host star, that the laws of physics impose limits that prevent such cosmic contagion. But even if the risk is theoretical, the idea forces us to confront how fragile our familiar reality may be. The notion that ordinary matter is not the most stable form is a reminder that our universe still hides truths that undermine the certainty of daily experience. The consequences of quark stars ripple outward in more hopeful ways as well. If they exist, they may serve as natural laboratories, offering us a way to study matter under conditions that no human machine can reproduce. They would bridge particle physics and cosmology, connecting the behavior of quarks with the evolution of galaxies. They would tell us about the earliest instance of the universe, when quark matter filled all of space before condensing into the particles that form stars and planets. In this sense, quark stars would not only mark the deaths of suns, but also echo the birth of everything. and they would invite us to think more deeply about the unity of nature. In quark stars, gravity, quantum mechanics, and nuclear physics converge. The collapse of a massive star becomes a stage where all the fundamental forces play together, shaping a remnant that embodies the deepest laws of existence. To discover them would be to discover that the cosmos is not only stranger than we imagined, but stranger than we could have imagined without the stars themselves to teach us. From practical consequences to philosophical implications, quark stars challenge us at every level. They ask whether matter has a deeper ground state, whether neutron stars are destined to become quark stars, whether gravitational waves and gamma-ray bursts carry signatures of transitions we have not yet deciphered. And they ask us to consider what it means to live in a universe where the familiar is only one possibility among many, and where the true foundations of reality may lie in forms we have never seen. Thus, the story of quark stars carries us beyond physics and into philosophy. They are not only objects of scientific inquiry, but symbols of how the universe hides its secrets. They remind us that every time we think we have reached the limit, we find another layer beneath. Neutron stars once seemed the end of the line, yet quark stars hint that the line goes further still. And so, as we leave the cosmic consequences of quark stars, we turn toward their role in the grander story of the universe. If they exist, they do not just affect stars or galaxies. They reach back into the earliest moments of time and forward into the fate of everything. The story of quark stars is not confined to the present cosmos, nor even to the deaths of massive suns. Their implications reach backward to the earliest moments of time and forward to the fate of everything. For if quark matter can exist stably in the heart of a star, it could also have existed in the primordial fireball of the Big Bang. And if it existed then, it may have shaped the path of cosmic evolution in ways we are only beginning to imagine. In the first microseconds after the universe began, all matter existed as quark-gluon plasma, a hot, dense fluid of quarks and gluons moving freely before cooling into protons and neutrons. In those instants, the entire cosmos resembled the interior of a quark star, only vastly hotter. As the universe expanded and cooled, quarks locked together into hadrons, building the nuclei that would later fuel the formation of stars. But what if not all of the quark matter condensed? Could pockets of it have remained stable, forming tiny primordial quark stars in the earliest era of cosmic history? Some theories suggest that during this transition, regions of space might have cooled unevenly, trapping quark matter in dense droplets. If those droplets were massive enough, gravity could have bound them together, preserving them for billions of years. Such primordial quark stars would be relics older than galaxies, fossils of the universe's first phase transition. If they exist, they might drift silently in the void, dark and nearly invisible, their only evidence the gravitational tug they exert on their surroundings. The possibility is astonishing, for it would mean that the universe contains stars older than stars, remnants not of stellar death, but of cosmic birth. These objects would not only test our theories of quark matter, but would also provide direct evidence of conditions that existed less than a millionth of a second after the Big Bang. To find them would be to hold a fragment of the infant universe in our hands, an unbroken link to the time when quarks first became protons and neutrons. Looking forward, quark stars also invite speculation about the long-term fate of matter. If strange quark matter is more stable than nuclear matter, then perhaps the universe tends inexorably toward its production. Neutron stars, given time, could all collapse into quark stars, leaving behind a cosmos where quark matter dominates. Billions of years from now, long after ordinary stars have burned out, the universe might be populated not by neutron stars or white dwarfs, but by quark stars. quiet embers of matter in its most fundamental form. In this vision, quark stars are not rare anomalies, but the ultimate state of matter, the resting place of baryons after eons of cosmic evolution. Their existence would mean that the universe itself prefers quark matter, that the familiar protons and neutrons of our bodies are only a temporary arrangement. In the deep future, all such matter might dissolve, leaving behind only quark stars and black holes, the twin monuments of collapse. Such thoughts lead inevitably to the grand questions of cosmology. What role do exotic states of matter play in shaping the evolution of the cosmos? How do the smallest particles decide the destiny of galaxies, stars, and worlds? If primordial quark stars exist, they may contribute to dark matter, the unseen mass that sculpts the structure of the universe. If future quark stars await, they may determine how the cosmos fades when ordinary stars are gone. The fate of the universe is bound to the fates of its smallest parts. To discover quark stars would be to glimpse both its beginning and its end. They would remind us that the cosmos is not static but dynamic, that its story is one of constant transformation, from quarks to neutrons, from neutrons to stars, from stars to quark matter again. The cycle would be complete, a symmetry across time, binding the birth of the universe to its far future silence. Quark stars, if they exist, could be among the most powerful tools for understanding the universe at its most fundamental level. They do not just affect astrophysics in the narrow sense of stellar death. They touch cosmology itself, because they may preserve and reveal conditions that once defined the entire cosmos. In the first fractions of a second after the Big Bang, quark matter was everywhere. The newborn universe was a blazing sea of quarks and gluons, so hot that no hadron, no proton or neutron could yet form. As expansion cooled the fireball, quarks confined themselves into particles, and those particles became the nuclei from which stars and galaxies eventually grew. This transition is one of the most important in cosmic history, for it marks the birth of ordinary matter. Quark stars offer us a way to look back at that transition indirectly. Their interiors recreate the same state of matter, not through heat, but through pressure. In colliders, we create the early universe in miniature, for an instant, with temperature. In stars, the cosmos does the same through density. If quark stars are real, they are not only laboratories of high-density physics, they are living echoes of the Big Bang, pockets of the early universe surviving into the present. Some scientists even speculate that quark stars, or smaller relics of quark matter, might help explain one of the deepest mysteries of cosmology: dark matter. Dark matter outweighs ordinary matter by a factor of about 5, yet it does not shine, absorb, or scatter light. Its identity is unknown. If primordial quark matter lumps formed during the cooling of the early universe, they might still drift through space as invisible bodies. Too faint to detect directly, they would nevertheless exert gravity, bending starlight and sculpting galaxies. This idea has not displaced the leading theories of dark matter, but it lingers as a possibility because quark matter, once formed, would be remarkably difficult to destroy. Quark stars also speak to the future of cosmic evolution. If strange quark matter is the ultimate ground state of matter, then the universe may naturally evolve toward it. Neutron stars, which appear stable on cosmic timescales, might eventually transform into quark stars, one by one, until quark matter becomes the dominant remnant of stellar death. Far in the cosmic future, when ordinary stars are gone, and white dwarfs and neutron stars have cooled into black lumps, the quark stars may remain, glowing faintly, still embodying the deepest state of matter. This perspective reframes the fate of the universe. It is not only about galaxies dispersing and stars dying, it is also about matter itself seeking equilibrium, finding the most stable state available. If that state is strange quark matter, then the ultimate universe is one where quark stars and black holes share the silence of eternity. If quark stars exist, they are not only relics of stellar collapse, they are also messengers from the dawn of time. The universe in its infancy was a cauldron of extremes, and quark matter was not exotic then. It was the norm. For a brief instant, after the Big Bang, everything was a sea of free quarks and gluons, a cosmic soup stretching across all of space. It was only when the universe expanded and cooled that quarks locked themselves into protons and neutrons, and those became the seeds of all ordinary matter. But the transition may not have been smooth. Cosmologists speculate that it could have been punctuated, with bubbles of hadronic matter forming in seas of quark matter, or with quark matter clumps trapped as the phase transition unfolded. These relics, if massive enough, could have survived to the present day as primordial quark stars. They would be older than galaxies, older than the first true stars, fossils of the earliest second of time. To detect one would be to peer not only into the physics of compact objects, but directly into the birth of the universe. Primordial quark stars, if they exist, would be difficult to find. They would not shine with nuclear fusion, nor would they beam like pulsars. They would lurk in the dark, detectable only through their gravity, bending light from background stars, or subtly disturbing the motion of galaxies. Some scientists have even suggested that quark matter relics could account for part of the mysterious dark matter, the unseen mass that dominates the cosmos. While this remains speculative, the idea is compelling, for it ties together two mysteries at once: the nature of quark matter and the identity of dark matter. If such objects are discovered, they will force us to rewrite the story of cosmic origins. We would no longer say that the first stars were simple fusions of hydrogen and helium. We would say that before those stars ever lit, the universe had already created quark stars, frozen embers of its first seconds, the light of galaxies, the structure of clusters, even the emergence of planets may have unfolded in a cosmos already seeded with strange remnants from the quark epoch. In the far future too, quark stars may be the last luminous bodies left, aside from black holes. As ordinary matter decays or collapses, quark matter could endure, a final form of stability. In this way, quark stars might bookend cosmic history, appearing first as relics of the beginning and last as survivors of the end. They would reveal not only what happens when stars collapse, but what happens when universes begin and fade. To contemplate quark stars is therefore to see the universe through a wider lens. They are not just possible objects among many. They are potential keys to the story of everything, linking the first moments of time with the ultimate fate of matter. To prove they exist would be to reveal that the cosmos itself contains deeper layers of truth, written into the stars, but pointing far beyond them. And so, as we leave behind the fate of the universe, we must also recognize what quark stars symbolize. They are more than theory, more than speculation. They are reminders that reality hides its greatest secrets in the most extreme places, that the cosmos is richer than we imagine, and that the beginning of time still echoes in the dense hearts of stars. From the moment quark stars were first proposed, they carried with them an air of the unreal, as though they belonged not to physics, but to imagination. Even neutron stars, when they were discovered in the 1960s, seemed to border on the fantastic. Pulsars flashing across the sky were so regular, so alien in their rhythm, that the first astronomers to detect them jokingly labeled their signal LGM for little green men. But quark stars go further still. They feel like something from the pages of speculative novels, too strange even for the boldest storytellers of the past. Part of their fascination lies in how they blur the boundary between science and fiction. We know neutron stars exist. We can measure their spins, their pulses, their collisions. But quark stars dwell in the shadows of theory, hinted at but never confirmed. To imagine them is to walk a line between fact and dream, where science provides the scaffolding and imagination fills in the details. That is the territory of storytelling, of myth-making, of the tales humans have always told to make sense of the unknown. Writers and visionaries have often reached for stars stranger than what science had confirmed. Long before neutron stars were measured, novelists conjured suns that collapsed into unimaginable densities, or worlds forged of exotic materials beyond steel or stone. The discovery of pulsars gave these ideas a scientific anchor, and soon neutron stars became staples of science fiction. Stories imagined civilizations harvesting their energy or using their intense gravity for time travel. Quark stars, though younger in concept, already inspire similar narratives because they represent not only the edge of physics, but the edge of possibility itself. One reason quark stars resonate with imagination is their duality. They are at once real enough to be plausible and strange enough to seem impossible. They are made not of unknown particles, but of the quarks we already know form the heart of every atom. Yet, arranged in a new way, those same quarks create a star unlike anything we can picture clearly. In that paradox lies their allure. They are both familiar and alien, both grounded and dreamlike. Consider what a quark star would look like to an observer. Not glowing like a sun, not crackling with the familiar colors of fusion. Instead, a smooth, bare surface of quark matter, radiating light with spectral properties unlike any star we have seen. The thought alone is enough to conjure images fit for cinema. Dark orbs adrift in the galaxy, glowing faintly with the afterheat of their collapse, waiting like cosmic riddles for discovery. It is no wonder that they capture the artistic mind as much as the scientific. And beyond their appearance, their implications are even more provocative. If quark matter is the ultimate ground state of matter, then everything around us, every atom in our bodies, every stone, every planet, is only temporary, perched above a deeper reality. Such a truth sounds less like physics and more like philosophy or even myth. It echoes stories of hidden worlds beneath the surface of the familiar, or deeper truths waiting to be uncovered. That resonance between science and story is why quark stars are as much symbols as they are hypotheses. Science fiction has always thrived on extremes. Black holes where time slows, wormholes that pierce space-time, civilizations born under red suns. Quark stars add another extreme to the list. They are the ultimate condensation of matter, the place where physics strips everything down to quarks and says, here, this is as far as matter can go before vanishing entirely. They are not just objects in space, but narrative devices, embodiments of mystery and transformation. When scientists describe quark stars in lectures or papers, they sometimes adopt the language of awe, as though even their equations strain against the uncanny. That awe is contagious. It is the same awe that has always drawn storytellers to imagine realms beyond the horizon, to people them with wonders and dangers, to use them as mirrors of human hopes and fears. Quark stars are the modern continuation of that tradition, born not from myth but from the equations of quantum chromodynamics, yet no less mythic in their impact. And so, as we begin to explore quark stars as cultural as well as scientific objects, we step into a territory where the boundary between fiction and reality dissolves. They remind us that the universe itself writes stories stranger than our own, and that sometimes science fiction is only the first draft of discovery. Quark stars slip so easily into the realm of imagination because they already sound like inventions of science fiction. A star that glows not with fusion, but with the afterheat of collapse, whose matter is not atoms but a sea of quarks, seems less like something found in a telescope and more like something dreamed up by a visionary writer. And yet, unlike fantasy inventions, quark stars are consistent with the laws of physics as we know them. That is what makes them so compelling to culture. They occupy a liminal space where science and story feed into one another. Writers have long been fascinated with the idea that the universe contains hidden states of matter or structures unseen by the human eye. The notion that beneath atoms lies a deeper world of quarks would have felt like pure speculation in earlier centuries, but now it is established science. To take that knowledge and imagine entire stars composed of quarks is to extend reality into narrative. It is no wonder that authors and filmmakers draw upon such ideas when building worlds, because they carry with them both credibility and mystery. In novels, quark stars have appeared as backdrops for cosmic civilizations, as sources of unimaginable energy, or as hazards drifting through space. The sheer density of such a star makes it an object of awe. A teaspoon of quark matter would outweigh mountains, and entire planets could be destroyed by fragments of it. To storytellers, this becomes a metaphor for hidden power, for the idea that the smallest constituents of matter hold forces beyond comprehension. In this way, quark stars join black holes and supernova as narrative icons, physical realities that double as symbols of transformation. Cinema, too, has borrowed the language of exotic stars, though often under different names. Films that speak of collapsed suns, of hyperdense remnants, or of strange exotic matter often dance around the edges of what we might call quark stars, even if the terminology is not used. Visual storytelling thrives on contrast, and few contrasts are greater than a glowing fusion star beside a dark, shrunken ember of quark matter. Such an image instantly conveys mystery and danger, even to an audience unfamiliar with the science. Artists outside of literature and film have also found inspiration in the concept. Painters and digital creators depict quark stars as luminous orbs suspended in cosmic night, surfaces smooth and alien, colors strange and spectral. In these works, the science is often secondary to the mood, but the effect is the same. Quark stars become emblems of the unknown, of the idea that the universe contains layers we cannot yet see. For audiences, such imagery resonates because it reflects our own sense of curiosity and humility in the face of the cosmos. The role of quark stars in culture also speaks to a deeper truth about human imagination. Whenever science reveals something new, imagination rushes in to explore its possibilities. When black holes were first proposed, they were regarded as theoretical oddities. Now they are central not only to astrophysics, but also to cultural imagination, appearing in countless stories as gateways, destroyers, or engines of mystery. Quark stars may follow the same path, moving from speculation to cultural icon as the decades unfold. What makes them especially potent is their strangeness. Black holes erase matter into singularities, but quark stars preserve it, distilling it into its most fundamental form. They do not represent annihilation, but revelation. They say, here is what matter truly is, when all other forms are stripped away. That message is not only scientific, but poetic, a metaphor for uncovering hidden truths beneath appearances. Writers and artists seize upon that metaphor because it mirrors the human quest for knowledge itself. Even beyond storytelling, quark stars influence philosophy. They invite us to ask whether the universe prefers deeper states of matter, whether what we see around us is only temporary, whether reality itself is layered more profoundly than we realize. Such questions echo through culture, through debates about stability, permanence, and transformation. The star becomes a symbol not just of physics, but of the instability of the familiar, a reminder that even what seems solid may dissolve under greater pressure. As we trace their role in imagination, it becomes clear that quark stars are more than astrophysical hypotheses. They are cultural mirrors. They reflect our fascination with extremes, our urge to narrate the unknown, our desire to find meaning in the cosmos. In that sense, whether or not quark stars exist in reality, they already exist in our imagination, shaping the stories we tell and the ways we think about our place in the universe. Human beings have always been drawn to the edges of possibility. The myths of ancient cultures are filled with images of worlds balanced on turtles, of fiery heavens and shadowed underworlds, of places where the ordinary rules of life and death are suspended. Quark stars, though born of equations rather than myth, resonate with that same deep impulse. They represent the hidden places of the cosmos, the strange domains where matter itself is rewritten. In that sense, they are as much a part of our symbolic imagination as they are of physics. When we imagine quark stars, we imagine matter reduced to its essence. The atoms that make up mountains, oceans, and the human body are familiar to us, their behavior woven into our daily experience. But inside a quark star, those atoms would vanish, stripped of electrons, protons, neutrons, until only quarks remain. It is an image of ultimate reduction, the peeling away of layers until nothing but the core remains. For storytellers, this becomes a metaphor for truth, for the idea that beneath appearances lies something more fundamental, more real. To poets and philosophers, quark stars can stand as symbols of clarity and revelation, of the universe laid bare. They also embody paradox. A quark star is unimaginably dense and heavy, yet tiny compared to ordinary stars. It is both immense and small, both stable and precarious, both ordinary in its building blocks and extraordinary in its form. Such contradictions are the essence of mythic imagery. Just as ancient myths spoke of creatures that were both human and divine, or places that were both land and sea, quark stars fuse opposites into a single entity. They force us to confront the limits of our categories, to admit that the cosmos holds realities we cannot easily classify. The strange contagion of quark matter, the possibility that it could spread from one star to another, adds yet another layer of symbolic weight. It echoes human fears of corruption, of contamination, of the fragile balance of stability giving way to hidden forces beneath. Yet it also mirrors myths of transformation, of ordinary beings elevated into gods, of mortals turned to stone, of worlds reshaped by contact with something greater. Whether we frame it as a threat or a revelation, the idea of matter transforming into its deeper form is powerful, and it resonates across culture. Even the very names we use, strange quark matter, strange stars, highlight their otherworldliness. Science often strives for neutral language, but here the vocabulary itself leans into the uncanny. A strange star is not only a technical possibility, but a poetic one, a reminder that the universe still contains the truly alien. It is no coincidence that such names capture the imagination as easily as they capture scientific attention. The fascination extends into the philosophical. Quark stars ask us whether reality is stable, whether the familiar world is truly the final word. If quark matter is more stable than nuclear matter, then everything around us exists in a metastable state, balanced precariously above a deeper truth. The comfort of permanence gives way to the possibility of transformation. This is not merely a scientific curiosity, but a philosophical challenge, echoing ancient questions about change, permanence, and the ground of reality. Such themes explain why quark stars feel as though they belong not only in laboratories and observatories, but also in libraries and temples. They embody the same mysteries that myths once did, translated into the language of physics. To contemplate them is to step into a space where science and myth overlap, where the cosmos reveals itself as both real and symbolic. And so quark stars remind us that imagination and science are not separate domains, but reflections of the same impulse. Both are driven by awe at the unknown. Both seek to illuminate what lies beyond sight. Both thrive on the strangeness of reality. Whether or not quark stars are ever confirmed, they have already enriched our imagination, offering new metaphors for truth, for paradox, for transformation. They are the myths of our scientific age, the strange stars that remind us that the universe is stranger than fiction. The power of quark stars to inspire does not stop at myth or metaphor. They also ignite visions of future exploration, of human encounters with cosmic extremes. Just as black holes have become symbols of ultimate frontiers, quark stars invite speculation about what it might mean to approach, to study, or even to harness such objects. Though these are dreams, they are dreams grounded in physics, which makes them all the more alluring. Imagine an age when humanity voyages among the stars, when telescopes are no longer confined to Earth, but carried on ships that skim the edges of neutron stars and beyond. A quark star, only a dozen kilometers across yet weighing more than the Sun, would be a sight of staggering strangeness. Its surface, smooth and bare, would glow faintly with the last heat of collapse, while its gravity would bend light into arcs and halos around it. To see such a thing with human eyes would be to encounter a reality stranger than any fiction, a cosmic relic that embodies matter stripped to its essence. Speculative technologies often draw upon such ideas. In theory, the density of quark matter suggests vast reservoirs of energy locked within. A fragment of quark matter, if ever extracted, could in principle outweigh entire cities, carrying with it the potential for power or destruction beyond measure. To science fiction writers, this becomes a story of temptation and peril. Civilizations seeking to harness the energy of strange matter, only to risk contagion, collapse, or transformation. To futurists, it becomes a thought experiment about the limits of technology, about whether there are realms of physics that should never be touched. Even without such fantasies, the idea of approaching a quark star challenges our sense of what exploration means. Humanity has long sought frontiers. The poles of Earth, the depths of the oceans, the surfaces of the Moon and Mars. But quark stars represent frontiers not of geography but of ontology, of existence itself. They are not destinations to be colonized, but mysteries to be contemplated. To dream of reaching one is to dream of facing the most fundamental question of matter: what lies beneath the familiar? In this way, quark stars fuel a deeper narrative about our species. They embody our compulsion to seek the strange, to push beyond boundaries, to stare into the abyss and wonder. They are reminders that exploration is not only physical, but intellectual and imaginative. Just as ancient explorers crossed oceans without knowing what lay beyond, so too do scientists and storytellers chart the possible existence of quark stars without certainty, driven by curiosity alone. There is also a sobering aspect to these dreams. Quark stars remind us that the universe is not built for our convenience. If strange matter truly is the ground state of matter, then all familiar things are precarious. The atoms that build us, the chemistry that sustains us, the stars that warm us are not the final word. They could, under the right pressures, dissolve into something alien. To confront a quark star is to confront that fragility, to realize that our reality may be only one layer in a deeper structure we cannot control. Yet rather than diminishing us, such realizations can enlarge our perspective. To know that the universe contains such strangeness is to be reminded of our place within it, small but capable of wonder. Quark stars, like black holes, are objects that dwarf human scale, but they also elevate human meaning. They show that our imagination is vast enough to grasp the unimaginable, that our curiosity reaches as far as the cosmos itself. In this sense, quark stars are as much about humanity as they are about physics. They reflect our hunger for mystery, our fear of annihilation, our fascination with transformation, our relentless urge to know. They are mirrors in which we see not only the strange heart of stars, but the strange heart of ourselves. To dream of quark stars is to dream of a universe that still holds surprises, a universe that is not finished revealing itself. And in those dreams, we find both science and story entwined. The physicist with her equations, the novelist with his metaphors, the artist with her visions, all are reaching for the same thing: to make sense of quark stars, to turn their strangeness into meaning. That act of reaching is what makes them powerful, whether or not they exist in the sky. Quark stars occupy a unique space in the human imagination because they are not just astrophysical hypotheses, nor just metaphors, nor just stories. They are all of these at once. In them, science and culture meet. Physicists propose them in journals, artists paint them in cosmic landscapes, writers weave them into tales of distant civilizations, and philosophers reflect on their meaning. They are the rare kind of idea that transcends disciplines, a meeting point where knowledge, wonder, and creativity converge. Part of their power comes from the way they refuse to stay confined. They began as equations on paper, as extrapolations of quantum chromodynamics into the densities of collapsing stars. But they quickly spilled into the wider imagination because their very description sounds like narrative. A star stripped down to quarks, a state of matter that could spread like a contagion, a relic of the earliest universe, a survivor of the end of time. These are not only scientific concepts, they are archetypal stories. They resonate with ancient patterns of myth and with modern patterns of storytelling, and in that resonance, they gain life far beyond the laboratory. The line between fiction and science has always been porous at the edges. Ideas once dismissed as fantasy, black holes, gravitational waves, even the expansion of the universe, later became established truths. The same may one day be said of quark stars. Until then, they live in both realms. They are fiction in the sense that we cannot yet prove them, but they are science in the sense that their possibility arises from known laws. They belong to that fertile ground where imagination prepares us for discoveries not yet made. In this way, quark stars also remind us of the role of imagination in science itself. Equations alone are not enough. It takes vision to see beyond the limits of experiment, to imagine states of matter that no human has ever touched. That act of imagination is not different in kind from the act of a novelist inventing a world. Both are forms of storytelling, and both are essential. Quark stars, real or not, embody the fact that discovery begins in the mind before it is written in the sky. They also embody the humility of science. For all our progress, for all our telescopes and colliders, we still do not know whether quark stars exist. We can model them, search for them, suspect them, but we cannot yet confirm them. They are a reminder that the universe is larger than our certainties, that the map of reality is not complete. To live in a universe that still contains such mysteries is both unsettling and exhilarating. It means the story is not finished, and neither is our part in it. Culturally, this uncertainty is what makes quark stars so powerful. They are not locked into textbooks or reduced to diagrams. They are open questions, mysteries alive in the sky. In that openness, they invite every kind of engagement: scientific, artistic, philosophical. They remind us that knowledge is not static but unfolding, that the universe is not a closed book, but a story still being written. And so we come to the end of this chapter, with quark stars standing as both science and fiction, fact and metaphor, physics and myth. They are the perfect bridge to our final reflections, because they embody the strangeness of reality itself. Stranger than neutron stars, stranger than fiction, They are the edge of what we know and the beginning of what we do not. The final step is to confront what it would mean to prove them real, to weigh the candidates we already suspect, and to ask what their discovery would mean for physics, for cosmology, and for us. If quark stars are confirmed, they will not only rewrite textbooks, they will rewrite our sense of the possible and remind us once again that the universe is stranger than we dared to imagine. The story of quark stars has brought us to the edge of the known. We have traced the lives and deaths of stars, followed matter as it collapses into ever denser states, imagined neutrons dissolving into seas of quarks, and considered the cosmic consequences if such transformations occur. Yet through all of this, one truth remains unshaken. No quark star has yet been confirmed. They linger at the threshold of possibility, not yet fact, but no longer mere fantasy, suspended in the liminal space between suspicion and certainty. The absence of proof is not absence of reality. The universe often hides its secrets well, and some of its most dramatic objects remained only hypotheses for decades before confirmation. Black holes were described in mathematics long before their shadows were imaged. Gravitational waves were predicted for a century before their ripples were felt in detectors on Earth. Neutron stars themselves were once thought improbable, too exotic to be real, until radio telescopes caught their regular pulses. Quark stars may simply be the next in this lineage, waiting for instruments sharp enough, data clear enough, and minds bold enough to recognize them. Candidates already exist. The compact star RxJ 1856.5-3754 remains an anomaly, with a featureless spectrum that defies simple neutron star models. The pulsar in 3C58 cools faster than theory allows, as though its core is shedding energy through unfamiliar channels. Other compact stars have radii so small or masses so peculiar that they strain the neutron star equation of state, hinting at deeper densities. None of these cases is definitive, but each is a piece of the puzzle, a whisper that something stranger than neutrons might be lurking among the pulsars. The next generation of observations may tip the balance. Gravitational wave detectors are becoming more sensitive, promising not just detections of mergers, but detailed readings of the structure of the colliding stars. X-ray telescopes sharpen their gaze, measuring the sizes and surfaces of compact stars with precision unimagined a decade ago. Radio arrays are mapping pulsars with exquisite timing, catching every irregularity in their spins. Each improvement narrows the gap between speculation and proof. What would it mean if confirmation arrives? The impact would be profound, reaching from astrophysics into the deepest levels of physics. It would mean that we have found a new state of matter in the sky, a state more fundamental than the nuclei that compose us. It would mean that the strong force, explored in colliders for instance, has revealed its true face in the hearts of stars. It would mean that neutron stars are not the final stage before black holes, but only one step in a ladder that descends further still. For humanity, it would be another humbling revelation. Just as the discovery of galaxies expanded our sense of scale, just as the discovery of black holes expanded our sense of extremes, the discovery of quark stars would expand our sense of matter itself. We would realize that the atoms of our bodies are not the most stable form of matter, that the universe harbors a deeper ground state, stranger and more alien than anything we touch. It would be a reminder that our place in the cosmos is provisional, that reality contains levels we have only begun to uncover. And yet, there is also beauty in that. To discover quark stars would not diminish the ordinary, but deepen it. It would show that beneath the familiar lies the unfamiliar, that the cosmos hides wonders waiting for us to grow wise enough to see them. It would prove once again that science fiction is often only the first chapter of science fact, and that the universe is stranger than our boldest imaginings. The final chapter of our journey, then, is not a conclusion but a culmination. It is the moment to bring together the threads of speculation and evidence, of imagination and observation, and to see quark stars for what they are, the strangest stellar remnants short of black holes, the ultimate frontier of matter, the places where physics bends and mystery begins. If quark stars are ever confirmed, the discovery will not simply be another entry in the catalogue of stellar remnants. It will strike at the foundations of nuclear physics, astrophysics, and cosmology, forcing us to rethink what matter is and how the universe organizes itself. Few discoveries could rival it in scope, because quark stars sit at the intersection of so many of nature's most profound questions. First, their existence would rewrite nuclear physics. For decades, the theory of quantum chromodynamics has described quarks and gluons, but most of its predictions at high density remain inaccessible to experiment. Colliders can only probe quarks at high temperature and low density, fleeting instants of freedom before matter recombines. If quark stars exist, they provide evidence that quantum chromodynamics permits stable deconfined matter at low temperature and extreme density. That would confirm entire sectors of the theory that remain otherwise untested, revealing that the true ground state of matter may not be the nuclei we have built our chemistry upon, but something stranger and deeper. Second, quark stars would transform astrophysics. At present, neutron stars mark the end of the line for collapsed matter before black holes. Their mass-radius relation sets a boundary, a frontier between stability and collapse. But if quark stars exist, that frontier shifts. It means neutron stars are only intermediaries, stars balanced on the edge of a deeper transformation. It means that compact objects in the universe may be more diverse than we thought, a spectrum that includes white dwarfs, neutron stars, quark stars, and black holes, each governed by different balances of pressure and collapse. The astrophysical zoo becomes richer, stranger, and more intricate. Third, the confirmation of quark stars would reverberate into cosmology. If strange matter is the ultimate ground state, then the early universe may have passed through a quark star-like phase, and remnants of that era may still survive as primordial quark stars. They may even contribute to dark matter, the unseen mass that sculpts galaxies. If quark stars are found, cosmologists will revisit their models of the early universe, looking for ways that strange matter influenced structure, nucleosynthesis, or the distribution of mass. The implications reach from the first second of time to the far future fate of galaxies. The proof would also reshape how we interpret gravitational waves. Already, detectors like LIGO and Virgo are capturing signals from neutron star mergers. If quark matter participates in these collisions, then the signatures we see are not merely about nuclear matter, but about quark matter itself. The confirmation of quark stars would transform gravitational wave astronomy into a probe of fundamental physics, turning every detected ripple into a laboratory for the strong force. The stakes are philosophical as much as scientific. To prove quark stars exist is to prove that the familiar is not final. The matter of our bodies, of planets, of suns, is not the deepest form, but only a temporary state. That realization challenges our assumptions of permanence, reminding us that even the seemingly stable is only a step along the way. It humbles us by showing that the universe contains truths hidden even within what we thought was most familiar, the particles that make us. In this way, quark stars embody the scientific journey itself. They remind us that every discovery leads to deeper mysteries, that every frontier is followed by another, stranger frontier still. Neutron stars once seemed impossibly exotic, then became common in our observations. Black holes once seemed too strange to be real, then became central to astrophysics. Quark stars may be next, stepping out of theory and into observation, changing our picture of the cosmos once again. The stakes, then, are nothing less than the rewriting of physics. If quark stars exist, nuclear matter is not ultimate, neutron stars are not final, and the universe is stranger than we thought. If they do not exist, then their absence is just as telling, for it will reveal that the strong force confines matter more tightly than we expected, refusing to let quarks roam freely at stellar densities. Either way, the answer transforms science. For now, quark stars remain suspects in the cosmic detective story. We have candidates, strange and stubborn stars that refuse to fit comfortably into neutron star models. RxJ 1856.5-3754 still shines with its puzzlingly smooth spectrum, and 3C58 still cools too quickly for comfort. Other compact remnants have measured radii so small that theorists raise their eyebrows and wonder if neutrons alone can explain them. But suspicion is not proof, and in the absence of certainty, the line between bold claim and careful caution is razor thin. This uncertainty is not a weakness of science, but its strength. It is the patience of astronomy that allows hypotheses to be tested over decades, even centuries, before consensus is reached. Black holes were once little more than mathematical curiosities, and pulsars were thought to be signals from intelligent life before their true nature was revealed. Quark stars may follow a similar path. For now, they live in the realm of possibility, suspended in that space where science acknowledges what might be true, but refuses to rush into proclamation. That tension between doubt and discovery is part of what makes the story of quark stars so compelling. On one hand, we crave the drama of confirmation, the decisive moment when an anomaly becomes a revelation. On the other, we respect the discipline of skepticism, the rigor that keeps science grounded. To follow the hunt for quark stars is to experience science not as a collection of finished facts, but as a living process full of uncertainty, debate, and hope. For the scientists involved, the stakes are immense. To confirm the first quark star would be to stand at a crossroads of disciplines, to contribute not just to astronomy, but to nuclear physics and cosmology all at once. It would be a discovery that textbooks would carry for generations, a moment that redefines what students learn about the universe. Yet the weight of that responsibility ensures that no claim is made lightly. Every anomaly must be tested, every alternative explanation exhausted, before the bold declaration can be made. For the rest of us, the meaning is no less profound. Quark stars represent our endless quest to peer beyond the visible, to uncover what lies beneath the surface of things. They symbolize humanity's refusal to accept that the universe is already known, that its mysteries are already exhausted. They stand as reminders that reality is layered, that there is always another level deeper, stranger, and more beautiful than the one we see. And this is why the possibility of quark stars resonates so deeply with culture, as well as science. They remind us that discovery is not just about facts, but about imagination. They allow us to dream of worlds stranger than fiction, while knowing that those dreams might one day become fact. They link the curiosity of children staring at the night sky with the equations of physicists modeling quark matter in their computers. They bridge the human longing for wonder with the cold rigor of science. Even if quark stars are never confirmed, their role in shaping our understanding will endure. They have pushed theorists to refine models of dense matter, forced observers to sharpen their instruments, and inspired new generations to ask questions. In this way, the search for quark stars is itself a discovery, a process that reveals as much about us as it does about the cosmos. But if they are confirmed, the moment will reverberate far beyond the walls of observatories. It will be reported in headlines, taught in classrooms, celebrated in novels and films. People will look up at the night sky with a new awareness, knowing that among the stars may lurk objects stranger than neutron stars, stranger than any sun, strange enough to remind us that the universe is far from ordinary. The candidates remain, the doubts remain, the search continues. And in that search lies one of the greatest scientific stories of our time, the hunt for quark stars, the possibility that the universe holds forms of matter beyond imagination, waiting quietly for us to see them. Imagine the moment when the first quark star is confirmed. Perhaps it comes from a gravitational wave signal, a ripple in space-time carrying the unmistakable fingerprint of quark matter. Perhaps it comes from an X-ray observation, a compact star with a radius too small, a surface too strange to be explained any other way. Or perhaps it arrives suddenly, with a burst of neutrinos and gamma rays, the signature of a neutron star collapsing into quark matter before our instruments. However it happens, the announcement would echo across the world. Scientists would be cautious at first, presenting the evidence with care, aware of the magnitude of the claim. But as the data is scrutinized, as alternative explanations fall away, a consensus would emerge. The first quark star has been seen. The textbooks must change. A new category of star has entered the universe of fact. The consequences would ripple outward immediately. In physics, the confirmation would lock down regions of quantum chromodynamics that have remained uncertain for decades. For the first time, we would know that quark matter is stable on macroscopic scales, that it can persist not just for trillionths of a second in colliders, but for billions of years in stars. The models of the strong force would be sharpened, theories refined, experiments on Earth reinterpreted in light of cosmic truth. The line between nuclear matter and quark matter would no longer be theory, but reality. In astrophysics, the discovery would expand the landscape of compact objects. Where once we spoke of white dwarfs, neutron stars, and black holes, we would now speak of quark stars as well, each with its own properties, its own role in the cosmic story. Supernovae might need to be reclassified, some ending in neutron stars, some in quark stars, depending on the mass and conditions. The collisions that produce kilonovae might take on new dimensions, with quark stars shaping the signals we see. Entire branches of astrophysics would shift to account for the new reality. In cosmology, the implications would reach even deeper. If quark stars exist now, then quark matter may have existed in the early universe, and perhaps some of it survived as primordial relics. The models of the first seconds of time would need to be revisited, the role of quark matter reconsidered. Some fraction of dark matter might even be explained by these relics, binding one of the greatest mysteries of cosmology to the discovery of quark stars. But beyond the sciences, the meaning would be philosophical. To prove quark stars exist is to prove that the universe holds deeper layers of reality than we had known. It is to show that the atoms of our bodies, long thought to be fundamental, are only temporary arrangements, and that matter itself prefers a stranger, more fundamental state. Such a realization shifts not only how we see stars, but how we see ourselves. It humbles us by reminding us that our reality is fragile, layered, contingent on conditions. And yet it elevates us too, for we are capable of glimpsing these truths, of imagining them before we prove them, of weaving them into the fabric of knowledge. The confirmation would also resonate with culture. Writers, artists, and filmmakers would seize upon quark stars as symbols of transformation, of hidden truths revealed, of the strangeness of the cosmos. They would appear in novels, in paintings, in films, inspiring a new generation with their mystery. The discovery would join black holes and pulsars in the pantheon of cosmic icons, bridging science and imagination, fact and story. And for ordinary people, it would change the way the night sky feels. To look at the stars, knowing that some of them have died and left behind quark stars, is to feel the universe deepen. It is to know that the cosmos harbors secrets stranger than fiction. that it is not finished surprising us, that we are still at the beginning of discovery. The first confirmed quark star would not be the end of a search, but the beginning of a new era. Once we know they exist, the hunt will intensify. Astronomers will search the sky for more, refining their instruments to map the population of quark stars, to measure their properties, to see how common they are. Particle physicists will re-examine their theories, adjusting to the new data. Philosophers will ponder what it means for matter to have deeper ground states. And humanity as a whole will take another step into the strangeness of the cosmos. That moment, when possibility becomes reality, will be one of the great milestones of science. It will stand alongside the confirmation of black holes, the detection of gravitational waves, the imaging of distant galaxies. It will remind us that the universe is larger, stranger, and more beautiful than we have yet dreamed. The story of quark stars is a story of thresholds. They stand between neutron stars and black holes, between the known and the unknown, between the familiar and the unimaginable. They are the children of collapse, the places where matter itself is pressed so far that it changes its identity. In them we glimpse the deepest workings of the strong force, the ultimate fate of neutrons, and perhaps the destiny of matter itself. Yet, even as we contemplate them, they remain elusive. No telescope has yet captured the definitive signature. No detector has yet announced the unambiguous signal. They hover just out of reach, like distant shadows at the edge of sight. That uncertainty is both frustrating and exhilarating. It reminds us that discovery is not guaranteed, that the universe guards its secrets carefully. But it also reminds us that we are still at the beginning, still learning to listen, still inventing the tools that will reveal what is hidden. If quark stars are confirmed, they will be the strangest stellar objects short of black holes. Black holes annihilate matter into singularities, swallowing even light. Quark stars preserve matter, but strip it down to its rawest form, reducing it to seas of quarks. They are not the end of matter, but its unveiling, a revelation of what lies beneath. They show us that the cosmos is layered, that the familiar is only the surface, and that beneath it waits something stranger still. This realization carries both awe and humility. It reminds us that the atoms of our bodies are not the ultimate form of matter, that our reality is contingent on pressures and densities. It humbles us by showing that the universe holds truths far beyond our daily experience. But it also elevates us, for we are the creatures who can imagine these truths, who can build theories that predict them, who can craft instruments to test them. To contemplate quark stars is to see the strange power of human curiosity reflected in the strange power of the cosmos. The legacy of quark stars, even before confirmation, is already profound. They have inspired scientists to push theories to their limits, to model matter at densities beyond experiment. They have inspired astronomers to search the skies for anomalies, to measure pulsars with exquisite precision, to listen for gravitational waves with instruments stretched to their limits. And they have inspired culture, seeding novels, art, and philosophy with their strangeness. They have already changed us, regardless of whether they exist. But if they do exist, then the story is only beginning. Their confirmation would open new frontiers of science, new avenues of exploration, new metaphors of meaning. They would become part of our cosmic identity, joining galaxies, black holes, and neutron stars as emblems of the strangeness of reality. They would remind us that the universe is not finished revealing itself, that the frontier is always further than we think, that wonder is endless. In the end, quark stars are more than stars. They are symbols of the strange beauty of existence, of the fact that the universe is deeper than our certainties, stranger than our fictions, richer than our imaginations. They are thresholds, mysteries, mirrors. They show us matter stripped to its elemental essence, physics bending at the edge of the possible, the cosmos whispering secrets of its hidden layers. And so we close with a vision. Somewhere in the galaxy, perhaps not far from here, a quark star waits. It glows faintly with the last heat of collapse, its surface smooth and bare, its gravity bending light into halos. It is silent, small, and hidden, but within it lies the truth of matter itself. To find it is to find not just another star, but a revelation. That the universe is stranger than neutron stars, stranger than fiction, stranger than we have yet dreamed. In quark stars, we glimpse matter stripped to its most elemental essence, a place where physics bends and mystery begins.